Being recorded.
Dr. Jane Costello as our first speaker in this webinar series. I don't want to take too much time away from her talk to introduce her, but I must say a few key things. She's a professor in the Department of Psychiatry and Behavioral Sciences at Duke, where she co-directs the Center for Developmental Epidemiology. She's also an adjunct professor in Duke's Department of Psychology and Neuroscience, and the Associate Director for Research at Duke's Center for Child and Family Policy. Jane was a principal investigator of the NIDA-funded multi-site Gene Environment and Development Initiative, GEDI, which brought together several longitudinal data sets to carry out cooperative GWAS and data analysis. And Jane is currently directing the 17th annual wave of data collection for the Great Smoky Mountains Study, a longitudinal study of the development of psychiatric and substance abuse disorders and access to mental health care in a representative sample of 1,400 children and adolescents living in the southeastern United States. I'm sure there's very much more that I could say about her, but now I will turn this webinar over to Dr. Jane Costello so that she can tell us, so she can make her presentation today. Jane?
Thank you, Erica. Can you hear me?
We can.
Oh, great. Good. Well, thank you for inviting me, and thank you to all this amazing number and select variability of people who've up to this webinar. I hope it'll be useful to you. Is based on many years of struggling with this issue of integrating data sets from multiple sources for genetic and other social science purposes. So let me get started. First of all, no potential conflicts. Secondly, what I'm going to say, a fair amount of it is based on two very important seminal papers, one from Jerry Reiter and his group, and another one from Patrick Curran and his group. And I think you're going to be sent these slides, and you can follow up on these papers, which I strongly recommend. So, as far as data integration is concerned, what is the issue for genetic studies? Well, clearly the issue is sufficiently powerful samples to assess genotype, phenotype, and envirotype across development. And when we say powerful, power resides in two main areas. First of all, in the number of subjects you've got, and secondly, in the quality of the data. And I'm going to be concentrating here very much on the numbers issue, but I do hope that I'll leave enough time to talk about data reliability, because it really is critical and something that I have to confess that genetics people have tended to ignore up to now. So, first of all, large numbers. How do we get them? Well, we either do enormous studies, or we try to combine smaller studies. And up to now, it's the latter that we've been doing more than the former, though we're moving more towards the former. So, what are the issues about combining smaller studies together? Well, first of all, the samples are going to be different from one another, or they may well be. Different age ranges, different races, different ethnicities, different social groups. The studies will very often use different measures. They often have different time frames, which again is something we tend to ignore, but is absolutely critical, we found. Does your questionnaire cover the last week, the last 2 weeks, the last 3 months, the last 6 months, the last year, or is it a lifetime diagnosis that you're making? It makes a huge difference. And of course, different scoring decision rules for both questionnaires and individual items. I'll come back to some examples of those. So, how do we deal with these problems? Well, one answer, as I alluded to, is have absolutely enormous studies that are all the same. This has not been the way that particularly the United States has gone, though other countries have explored that route. And given that we're talking about America here, let's assume that we're talking about cobbling together small studies. How do we do that? Well, here are some methods, and I'll be zipping through these quite fast. assuming that you can go back and look at the slides and pick up the references as we go. So I have so far identified three various approaches to this: data federation, data virtualization, and data harmonization. And then as far as data harmonization is concerned, there are a bunch of different ways that this can be done, or people have tried to do this. So let's get going and go through this list. So data federation, this is defined as warehousing or reporting or creating dashboards or mashups or portals, or it's sometimes called master data management or data services in service-oriented architecture or SOA, or post-acquisition systems integration, or as we probably know it better, cloud computing. And what happens in data federation is the data is collected from distinct databases without ever copying or transferring the original data itself. And the system of data federation collects metadata, that's data that describes the original data, and puts it into a single database. And this is the thing that the NSA is very good at doing. This is a picture of it, just for fun. Data from all these different places come into the database and then can be pulled out again to use to answer various questions. So data federation, I'm not spending long on that because I don't think it's a method that we're going to be using for genetic research anytime soon, although you never know. At least I misspoke myself there. It might be used purely for genetic purposes, but it's not going to be very useful for the kind of thing we're talking about here: gene, environment, development, analyses where you need information about the phenotype, the envirotype, and development, as well as the genes. So our second type of data collection is called data virtualization. And this allows the application to retrieve data and manipulate it without requiring technical details about the data, such as how it's formatted or where it's located. So the data remains where it is, and access is given to it by the owner of the data for, as it were, the data virtualization mechanism to come in and look at it without messing it around. This means that the data is relatively safe from errors, and it limits the workload. And the other thing about data federation is that it doesn't impose a single data model on the data set, which data federation does. I see I've got a bunch of notes, a bunch of comments here, but they all seem to be about being able to hear or see about what I'm actually saying. So I don't know, Nora, is there anything we can do about this? A lot of people don't seem to be able to hear me.
One thing that helps is using your handpiece, your earpiece. Pick up the receiver. It's clearer. If you're on speaker, you're a little far off. If you can use your receiver on your phone, it should be better.
Well, okay. Well, I put the volume up here. Perhaps that'll be better. Okay. I was talking about data federation and data virtualization, and this slide that's on the screen now is an example of something that we're developing at Duke at the moment, which is a portal whereby people can explore the characteristics of different data sets. In this case, this is a bunch of longitudinal developmental data sets that we have at Duke. And people who want to know about them and whether they could be combined can look at this and explore it and see what age the subjects are, and how many there are, and what mental health measures, what parenting measures, what stress biomarkers are in all the data sets. So this is an example of a study comparison tool that is in itself, again, an example of data virtualization. Okay. So pros and cons of data federation and data virtualization, which I'm not going to say anything more about, is that they kind of are useful for hoovering up enormous quantities of data, as we know from the fact that everybody knows about what's on our credit cards. But they don't capitalize on joint characteristics of the data. They're designed more to look at individual data sets or parallel data sets rather than to pull them into one study. They don't study moderators of effects. You can use them to look at the basic data, but not to look at moderators. And they don't, at least as they are at the moment, seem to be the kind of thing that we're going to need for GED studies. That's Gene Environment Development Studies. However, there is a lot of software available. These are just some examples of software that is currently available for sale for analyzing data using either data federation or data virtualization. And that's all I'm going to say about those methods. I'm going to get on to data harmonization, which is something we've played with more, I think, in the area of gene environment development, data analysis. So data harmonization. These are a set of methods for integrating data, that's integrating it, where data sets containing variables that tap, when data sets contain variables that tap similar constructs obtained using different measurement instruments. So, and there are a bunch of these methods, and I'm going to go from the simplest to the most complex. So the simplest is transform and recode. And what this simply means is if you've got one data set where female is coded as 0 and male is coded as 1, and you've got another data set where female is coded as S and male is coded as M, you simply transform and recode them so that in your new data set, shall we say, female is coded as 0 and male is coded as 1, or whatever you want to do with it. So that's a simple transform and recode. It's so simple that you probably wouldn't think of it as a method of data harmonization, but it's the basic one, and it's used a great deal in multi-site genetic studies, where you might be looking at cases of schizophrenia, for instance, and they've all got a different code for schizophrenia, so you have to transform them all into a simple single code for schizophrenia. It's simple, it's powerful, but it makes huge assumptions. For instance, if you're doing a genetic study where you're pulling together all the cases of schizophrenia in your 200 different data sets, you're making the assumption that schizophrenia in your data set is the same as schizophrenia in my data set, as it is in schizophrenia in Robin Murray's data set in London. And as we know from the work that back in the 1930s, schizophrenia diagnosed in England is a very different animal from schizophrenia diagnosed in the United States. So that using a simple method like transform and recode is to make enormous assumptions about the quality of your data. A rose is a rose is a rose. And that's all I'm planning to say about transform and recode, unless there are questions later on. So the second type of data harmonization is what's called aggregated data meta-analysis, and this too I think you'll all be familiar with. This does the business of identifying consistencies among and accounting for the variability observed across studies that have attempted to address similar substantive questions. So in a traditional aggregated data meta-analysis, an overall summary statistic, or an effect size usually, is collected from or computed for each of the sample data sets. And then statistical methods are used to estimate an effect size for the whole population of relevant data sets. And I expect you can, all of you, think of an example of a meta-analysis of this type. Here's an example of, this is not specifically genetic, but this is a meta-analysis of studies of the prevalence of attention deficit hyperactivity disorder in more than 60 studies, starting with 1985 and going on to 2014, done by Guillermo Polancic. And the size of the circles represents the size of the sample, and as you can see, they're all over the place, but the interesting thing for epidemiologists anyway is that the prevalence of ADHD, once you've accounted for all the differences amongst the data sets that I talked about before, like the time frame of the interview and whether it's DSM-4 or DSM-5 or whatever, once you account for all those things, the prevalence of ADHD has stayed absolutely flat for the last 30 years. So that's an example of a meta-analysis using studies. The things to note about that, if you think of it as a method for doing genetic research or anything else, is that it uses study-level data, not individual-level data. So it throws away an awful lot of data. And it's also dependent on what's been published, or, more importantly, probably what has not been published, what's gone into the waste bin. So it gives a very biased view, probably. We can't even estimate that, but it probably gives a very biased view of whatever it is it's estimating. So it's probably not a very useful method for genetic research unless it's all we have. So let's move on from meta-analysis to meta-analysis. Here what people have done, or try to do, is to come together data sets, identify common variables in all their data sets, and carry out, as it were, parallel analyses using the same sort of statistics in each study. We actually had a grant from NIDA to do this a long time ago, before people realized it wasn't a very good approach. It has its advantages. It integrates the data at the individual subject level rather than using summary statistics across studies. And it's definitely worth a try if you have no money or time to do anything else. However, as we found when we tried it, it can be extremely labor-intensive, trawling through multiple data sets to find if you've got exactly the same variable. And the fact that so few studies have been published using meta-analysis suggests that it hardly ever works. It certainly didn't for us. We tried it with, I think, 8 data sets and ended up with a paper we've never succeeded in getting published. Mm. So it was not a very useful activity. So moving along, I'm now going to talk about 2 methods that are currently being researched and worked on. Interestingly, both in North Carolina, one at University of North Carolina, Chapel Hill by Pat Curran and Andrea Husson and Matt Bauer, and one at Duke by Jerry Reiter and his colleagues. And the first of these is known as Integrative Data Analysis, or IDA. IDA uses a latent variable approach. That is, it presumes that there is an unobserved latent propensity underlying the data that gives rise to the observed measures across individuals and across multiple samples. Where data sets to be harmonized include largely non-overlapping items derived from different instruments, you can compare measurement using, for example, item response theory. I'll talk about that a bit more, which can allow for equating, scaling, and linking different measurement instruments across items across samples. And then the resulting parameter estimates are used to produce latent variable scale scores for all the participants in the combined data sets using a confirmatory factor analysis approach called ML, what's its name? I will tell you what its name is when I can remember. Well, we'll come to that in a minute. Anyway, it's a variant on a confirmatory factor analysis approach, or an IRT, measurement model approach. So first of all, what you do when you're doing an integrated data analysis is you figure out what your question is. And you might be trying to replicate a genetic finding, or you might have a novel hypothesis that you want to test. And then you identify the data sets that contribute to it. Then you develop a pool of potential items across the data sets. It's very, very, very much better to have some items in common across the data sets, but not all items need to be identical across all studies. And there are two types of analysis done here. The first is if all your items are in common, and we call that a common analysis. And another one where you can compare and come up with some common commensurate data analysis. I'll show you examples of those in a minute. And you fit a measurement model to test structure and the invariance using IRT, as I said, or a variant of factor analysis. And then you create a new score for each subject based on your, and use that in subsequent analyses. Here we are. This is what it's called, moderated. I've forgotten the moderated bit. Moderated nonlinear factor analysis. And it's described in one of Pat Curran's publications. So what you're doing is taking a STEM item or response and altering it to make it comparable with similar items in other studies so that you can do a pooled analysis. And this is an example. Here we've got consumption of alcohol is our concept, and it's defined differently in 3 different studies. So we have to look at these 3, argue about them, and come up with a harmonized item, which is called past year frequency of alcohol use. Similarly, you very often find that different studies use different response scales. One study uses days per month, another one has a 0 to 7 time scale, and the third one has a 0 to 9 scale. Numbers don't add up, because 4 on this scale is 1 to 3 times a month, whereas a 4 on this scale is once or twice a week. So what has to be done is to create a harmonized item on which there are data from all the studies. So if what they've done here is create a scale onto which you could map these other scales. So that's data integration in a nutshell. It's very adaptable. You can test a lot of different hypotheses with it. However, it is its limitation is if there are only a few items that overlap across the data sets. In fact, you can't do it if there are no overlapping items. And if there are a few, it becomes much weaker. And the other characteristic it has is highly sensitive to the psychometric model that underlies it, the factor analytic or IRT model underlying it. So you may be making huge assumptions which your data won't bear. Finally, we have multiple imputation. And this approach, which is the one that people at Duke have been developing, is a method that treats data harmonization as a missing data problem. So here's how you think about that. Here are your three data sets, 1, 2, and 3. And these are the same three data sets that I'm going to compare. I compare data set 1 with data set 1. Variable A is in both of those because they're the same data set. Similarly, variable B is in the second data set, and variable C is in the third data set. However, data set 1 is missing variables B and C. Data set 2 is missing variables A and C, and data set 3 is missing variables A and B. So we've got a lot of missing data. How can we use this mess to produce something which we can do joint work? Well, the answer to this is to collect a calibration data set, a new data set, which includes variables from all the data sets to be harmonized. To create a file including all those data sets and the calibration data set, and then to perform multiple imputation on the combined file, which is a standard method of working where one has missing data. So here's an example. We have three data sets, actual real data sets, the Ad Health data set, the Child Development Project, and the Great Smoky Mountains Study. And we're going to create a new data set. We're going to go to a research panel managed by an organization called Knowledge Networks, and they're going to generate for us a sample which matches the samples that we're using from those three studies. In this case, although these are all longitudinal studies, for this example, we're just using the data from the subjects obtained when they were 19 or 20. And what we're looking at is measures of alcohol use and measures of association with deviant peers. So the question that we're asking is, are people who have deviant peers more likely to be using or abusing alcohol? And as happened before in the other example, we've got different questions using different language and different response options, both for the alcohol use and for the deviant peer use. So there's nothing that you could directly map one-on-one in these three studies. And that is pretty much always the case in my experience. So a calibration study will take something, in this case we use the audit, which is a widely used questionnaire about alcohol and drug use. And using the same procedures that the original studies used. So for Ad Health, we used an online survey. For Great Smoky Mountains Study, we used a telephone interview. And the new panel, the knowledge panel, were asked all the questions that were relevant to our main issues from the other studies and the new measure, the audit. So we have from the Ad-Health study, we have a limited amount of data. From the Child Development Program, a different limited amount of data. From Great Smoky Mountains Study, a different limited amount of data. And from the new calibration sample, the answers to all those questions and the new gold standard audit. So what the researchers then did was to use CART, classification and regression tree, which is a form of data analysis that some of you will be familiar with, I expect, but it's widely available in the big data analytic packages to figure out where to impute the scores that were missing on the 3 real data sets. So using CART, you can regress each variable with missing data one at a time on all the other variables in the combined data sets and draw values corresponding to the missing data. And you do this many, many times. In this case, it was done 100 times, which reflects the uncertainty associated with imputed data when you're working with a missing data model. And this is just to give you a glimpse. The cross represents the real answer, the real mean score from that sample to that question. So this is a GSMS question, and this is the mean from the real GSMS sample, and this is a plot of the replications from the imputed data. And as you can see, the mean for the real sample is comfortably inside the range for the imputed data, and the same for Ad-Health and the same for our development project. So you can argue that this worked. In this particular case, this methodology worked in that using imputed data based on a calibration study, we got a range of values that are comfortably surrounding the actual answers that we got from each data set to its own question. So that basically says what I've already said. So let's skip that. And think about whether this is a good technology. It makes sense intuitively to me. It reduces reliance on possibly unverifiable modeling assumptions such as you have to make using IDA and transform and recode, come to that. However, it does have serious drawbacks, and one of which is that it's extremely expensive. I think we put a couple of $100,000 into creating the calibration data set for this particular study. And of course, each different set of variables may need a different calibration, different calibration sample. Plus, there are some things it's very difficult to get a calibration sample to do. So it's going to be almost impossible, I suspect, to go out and get DNA to do a calibration study, and terribly expensive to do if you wanted to use this approach. So you could use it to harmonize other variables, but not your genomic variables. It also makes some assumptions. It assumes that the relationships in one calibration sample apply to other calibration samples. It assumes that variables missing in the basic data sets are missing at random. And it assumes that difference in data collection methods, for instance, the telephone versus the online methods we used in our study, don't matter. So it's of data integration. It makes serious assumptions. So as far as pooling data sets concerned, some preliminary conclusions. Phenotype or genotype may well be measured differently across studies, but even if you've used the same platform and the data was assayed at the same lab, even in spite of that, you're going to have major differences across studies in the assessment of the phenotype and of the environment. IDA and data imputation are the two harmonization methods that have the most promise, but they are both of them expensive and time-consuming. And they both of them create a bunch of assumptions which we haven't yet tested. So none of them is perfect. So that's where I am. That's what I want to say about data harmonization. It sounds so much easier than it turns out to be, and it may be necessary because we just don't have the big data sets, but it really is a painful process and needs a lot of thought. However, I want to make one other point, and that's about reliability. I said at the beginning, how do you increase the power of your study? And there are two ways. One is to increase the sample size, and the other is to increase the reliability of your data. I'm sure all of you who are psychologists remember learning this, your very first psychology statistics class. So how do we get more reliable data? Well, we've talked about quantitative factors, the magnitude of the interaction. Well, we haven't talked about these, but these are other quantitative factors as well as the size of your sample. The magnitude of the interaction, the allele frequency, and the strength of the association in those with a common allele. Those are all quantitative factors which will influence how reliable your data are. But there's also reliability is also dependent on the quality of the data, the quality of the type, the quality of the environmental factors. And by quality, I'm talking here about reliability. And by reliability, I'm mainly talking about test-retest reliability, not inter-rater reliability, not internal consistency reliability, but test-retest and the aspects of reliability that are subsumed under validity. The two concepts, we tend to treat them as if they're very separate, but in fact there are various aspects of reliability that could just as well be called validity. So what I'm talking about here is that we'll get more reliable data if we have repeated measures of the same subjects over time. We will have more reliable data if we avoid using a lifetime history. Did you ever have X or Y? We will get more reliable data if the phenotype and the envirotype are measured on the same subjects. We will get more reliable data if we use measures of known good test-retest reliability. And data will be more reliable if we can test the relative dating of exposure and onset. These are all aspects, or most of them are aspects of longitudinal research, which can improve the reliability of one's assessment. Here's an example of what difference reliability makes the power of your study, the number of subjects you need. Jumped around, and I can't move it. Well, you'll just have to imagine. So let's say that RTX is the reliability of environment or the exposure. And let's say that RTY is the reliability of the phenotype. RTX goes across here and we measure our exposure with a reliability of anything from 0.3 to 0.9, and we can measure the reliability of the phenotype at different levels of reliability. Now, if both of these is poor, let's say that the reliability of the phenotype measurement is 0.4 and of the exposure measurement is 0.3, in order to detect a significance level of 10 to the minus 4 with 95% power, I'm going to need almost a million subjects. If my measurement of both those is much stronger, let's say 8 for reliability of phenotype and 0.9 for the reliability of the exposure, I will have the same amount of power with a sample of 16,000. Sorry. And similarly, if the allele frequency is 0.25, and I go down from 151,000 to 1,800 in the number I need, same power. And this you can find in a paper by M.Y. Wong, written in 2004. I strongly recommend it. So what that tells us is there's an 80-fold difference between using two weak measures and using two strong, reliable measures in the number of subjects you need to draw the same conclusion. So how do we get more precise, more reliable measures? Well, I said it before, but I say it again. Repeated measures of the same subjects at frequent intervals. This is always provided that the error in the repeated measures is not correlated. Reliable instruments and measures that validly reflect the construct of interest. This is where validity and reliability kind of hold hands, because a reliable instrument is more likely validly to reflect the construct of interest. Now, how do we get these qualities in our data? Well, existing longitudinal studies are remarkably useful for this. They are, however, extremely expensive. Just to give one example, the study that I've been working on has been going on for 20 years, and I estimated that NIMH and NIDA between them have spent about $30 million on the data that we have. Money to put out now. Dataset is there, it exists, and there are not many, but several others with data that have been collected over time. Turn out to be extremely valuable commodities that we shouldn't cast away lightly. So final comments. If I've used up all my time. So we've tried all the cheap ways to integrate data. We've tried lots of small samples. We've tried cross-sectional studies. We've tried studies where we've nothing in common with the variables. We've tried studies with really crappy measures like administrative data sets or lifetime diagnoses, or using what are politely called screening questionnaires for phenotypes, where we use 4 items to diagnose a case of schizophrenia. And basically you get what you pay for. You get very disappointing results. And so my take-home message here is that NIDA already has data sets that can be used for integrative GED analyses. It already has put money into developing these methods of data analysis, IDA and data harmonization using missing data methods. Neither is quick, neither is cheap, but it's a lot quicker and a lot cheaper than funding another 20 years of longitudinal research or the kind of size of data set that the geneticists are asking for nowadays. So I'm recommending that we go back and think carefully about the best use we can make of data that's already been collected. And thank you very much for listening. Now,
if anyone has questions for Dr. Costello, please send them in now via the appropriate place on your webinar screen, which is probably the bottom left.
and if you don't want to do it now, you can always email me when you wake up in the middle of the night with a question.
Well, we have gotten one comment at least, which I think you can see on your screen, that some of the participants want to thank you for your webinar, which we, of course, echo. I find it hard to believe nobody has questions, but perhaps you explain things so thoroughly, Jane, that we're all good.
I think it's more likely that people are just defeated, completely defeated.
I hope not. I was very excited to hear your last part about the need for, as a developmental psychologist, I'm very fond of longitudinal studies, and it's always nice to know that they're being advocated for further use and future use.
Well, they go into fashion and out of fashion, and they've been out of fashion rather recently, I think. But one thing that's made them enormously valuable that we didn't know about before is epigenetic studies. And we just have one that we're working on with folks at Virginia Commonwealth University, where we're able to use the longitudinal quality of the data, because we've got multiple assessments and multiple blood samples over time, to look at the epigenetic effect of trauma, being able to look at the samples before children experience trauma and after they've experienced trauma, and look and test for epigenomic changes.
That's really exciting. That's great.
Which is something you could not do without longitudinal data, I don't think.
Absolutely.
Okay.
If there are no more questions, and nobody is going to write in with questions in the next couple of minutes, or do you have any final comments or anything that you'd like to add, Jane?
Ben wants to know if it's possible to get a copy of the references. The references, the main ones, are in the slides, which if he's... yes, he is.
We'll be sending the slides to all participants once the webinar is over, so everybody will get those.
Good. That's it then.
All right, well then I want to thank you very much, Jane, for being the first participant in this webinar series. I think this was a great way to kick off this series. Thank you for your time and your patience with the technology. Oh, wait, we have a question. One moment.
Yes, Colleen says, is there a principal difference between the data we deal with now, or is it we just have more of it? Well, we certainly have more of it. I think we're paying more attention to some of these issues. Colleen, I don't think the data are different. It's just the way we're thinking about them that's different, I would guess. Okay.
I think on that case, then, we will thank you for a wonderful afternoon. We appreciate your time and your attention to this. And thank you for all the participants. We had a great number on on the line listening in, and we will also be posting this later on our website so that people can go back and watch and listen to it later on as well. So thank you everyone for your participation, and have a wonderful rest